Good morning, and thank you all for the opportunity to speak to you. I usually start these talks with a bit of a confession. I'm not a mining engineer. I don't know all the ins and outs of a mine or the technical terms, so please bear with me if I use some of those expressions wrong. However, I am an engine developer. I am a guy that works with engines and engine tech, and the company Orbital has been doing this for almost as long as these awards are going for well over 35 year history. We are also from Western Australia, so don't shoot me. We are from the other side of the country. Okay, you guys have a lot of challenges when you're developing product for underground mining. It's a fairly dangerous environment. You've got to have surface temperatures below the ignition point of coal. You are having product that has to be certified to be explosion proof. You're dealing with environments, as we heard from Fiona, that have methane, ethylene, all these combustible byproducts there as well. And of course, you're after the protection of your workers. So you're looking at the technology that can control particulate emissions, ultrafines, as well as gaseous compounds. Today's presentation, I'd like to review some of the key findings of the ACARP work that we've been doing. 2 projects to date, and I'll leap from the first project to the second project. I'd like to share some of the particulate and emission results there and some of the challenges that we've had. Today, the solution of choice is to use wet filters as a means of collecting the particles out of the exhaust and preventing them from entering the enclosed environment of the underground space. The future, it will be disruptive. It will be probably electrically powered machines, just like electrically powered machines have been implemented in your longwall processes. But for now, the diesel engine is with us as a mobile transport solution. For now, we need to solve the emissions of that engine at the point source. Ventilation is a remedy, it is not the solution. So a little bit about ACARP, and ACARP has sponsored this project. Many of you will know ACARP. You are members of ACARP by virtue of being miners. Some of your product proceeds actually go back into the bucket that is dished out to companies for research and development. Our first project was a fundamental research project. It looked at the proof of concept level. Our second project is applied, so we're actually looking at the industrialisation of that solution. Mentioned there are our industry monitors that have walked us on this journey. Great support from many mining companies. And without them, without that collaboration, we wouldn't have been able to apply some of these technologies to the mining environment. So what was the plan? Of course, plan number 1 was to establish ways of improving worker health and ensuring that there were good solutions for maintaining air quality, robust tamper-free solutions where we could reduce particulates at the source and ensure that there was no excursions in these levels that we were attaining. The approach taken was to have a sealed wall flow DPF technology and to work hard to match the way that that technology performed with the duty cycle of those machines. There's no point having technology that tells you to run a machine a different way. It had to work with the machines as the way they run. These machines generally, as you'll see from some of the data we'll present, run a fairly low duty cycle, long periods of idle, and that doesn't help a lot of technology work. The other thing that we were doing in the background was identifying ways of reducing the total cost of operation. At the moment, the solution of replacing filters on a shift by shift basis, or sometimes more often than one shift, is economically challenging. There are environmental issues as well as disposal and things like that. But the biggest risk is people forget to put these filters in, or people take a shortcut. And because it's not tamper-proof, you can't guarantee the outcome. So I'll jump straight in with some of the results, and these were identified fairly early on in our fundamental ACARP project. And the capability of a diesel particulate filter to reduce particulates is unquestionable. The bars there in grey are the results of an engine out emission level, and the little bars there in red are the results when you have a diesel particulate filter installed. The graphs there with the green labels, NRTC and NRSC, they're the regulatory standards. But what we did as part of the project is look at how the machines are being used and then test in a dyno environment, in an engine dyno environment, how the diesel particulate filter worked when you use the duty cycle of the machine working in the real world. And you can see the same sort of benefits being achieved or exceeded. So what is a wall flow diesel particulate filter? And I'll take a couple of slides just to explain the technology for those that are not familiar with it. It consists of two parts. Firstly, there is a catalyst, and the catalyst is a flow-through honeycomb of ceramic with a wash coat of precious metal, platinum, palladium, something like that. The diesel particulate filter itself has the same structure, it's a honeycomb, but every alternate hole is blocked from one end or the other end. And it means that the gas has to go through the wall to get out the other side. And that's hence its name, it's wall flowing. It flows through the wall rather than flowing through the holes. I'll have to have a slide on chemistry because this is a technical event, but I won't make it too deep in detail. Once you store the soot on a diesel particulate filter, how do you get it out? How do you get that carbon out? There's no point having a sponge if it blocks up, so you have to regenerate that sponge. Now this is where technology called CCRT, continuously catalytic regeneration technology, comes into its own. The first level of regeneration is pure oxidation. You have carbon, it finds some oxygen. If you've got the right temperature, 600 degrees Celsius or thereabouts, it'll burn off, and that carbon will come out as CO2. But a diesel engine doesn't reach those gas temperatures very often. It does at full load, but as we know, we don't use the machines that often at full load. So we need an enabler, a little bit of an assistant, and that comes through using NO, nitrous oxide, as a carrier for additional oxygen. And in combination with the NO2 that's formed and the reaction with carbon, we're able to get that oxygen to jump across a lot easier and to do so at lower temperatures, at 250 to 300 degrees Celsius, which is typically the operating temperature of exhaust coming from a diesel engine. So how do we fit that system in there? This is your typical disposable filter system. There's a water scrubber there that cools the exhaust, and then that wet exhaust now goes through a filter, a paper element filter typically, sometimes it's glass fibre, and that catches the particles. The way the system is reconstructed, that water scrubber is still there, so you can meet your tailpipe temperature requirement and then bring that temperature to below 70 degrees, and the diesel particulate filter is installed upstream of that, straight out of the engine, to get as hot a gas as possible going into it. Now, we're dealing with chemistry that requires temperature, so developing that in a mine environment is not necessarily smart, and it's also quite dangerous, and it's also quite an iterative process to do this. So rather than develop in a mine and burden the business with the cost of development, what we did is we took the process offline, we measured how the machines worked in the field, took that data and created some cycles to represent that and ran that in a dyno environment. We could iterate through the development process effectively without any of the dangers. And then occasionally go back to mine and re-qualify that those solutions were heading in the right direction. The first step was to characterise the duty cycle of the fleet. There are different mining operations. You guys are mining people, I don't need to explain those, but some applications the machines get worked harder, in other applications the machines are quite lazy. The cycle we developed to represent the way an LHD works, there were two cycles we came up, steady state and transient. It's really the transient one that governs the performance of any system, because that's the way it works in the real world. It doesn't sit there at one speed and one load all day. It actually jumps between these things and the temperatures move around. The walk away from this data, and this data has been published in our first ACARP project, is that about 50 to 57% of the time on an LHD is spent idling. And when you idle an engine, that's low temperature exhaust. That's not conducive to regeneration. So you have to do some special things there to make it happen. The second challenge is, of course, demonstrating that you can have this hot thing inside where the temperatures are being used to make the catalyst reaction work, but yet you can maintain a cool surface temperature. And the graph here shows some of those preliminary results where we did have hot exhaust, in some cases up to 600-700 degrees gas temperature, but on the surface we were able to be compliant through a means of having an insulation layer around that DPF. Now, insulations are not a brilliant, novel way, nothing truly inventive about that, but it did two things for us. Firstly, it kept the heat in, so when we didn't have a lot of heat, like at idle, we actually amplified that heat. And secondly, it reduced the burden of the cooling that would normally be required, that is normally taken on by the radiator of the application. So when you wrap an exhaust in water, you're really wasting all that heat and you're putting the burden onto the machine. So the first project, the 25073, was completed in 2016. The results have now been published, available from the ACARP website. That project ran fairly smoothly and straightforward. It led to the second project where we were looking to industrialise that system. So we had a great proof of concept approach. We'd done one site trial just to measure some numbers and compare some numbers. And the second project was really about, can you actually build this? Can you build it in quantity? Can you actually make it safe enough to be compliant and achieve the necessary certification? We're in the final stages of that. There's still one significant site trial to do, and then some pre-certification work needs to be, polished up. We've done the basics and confident that it is working. So we expect to complete this project by the end of the year. The first question that gets asked is, will this filter block up? And that's a good question to ask. It is a ceramic, it's porous, it will collect the black stuff. If we aren't operating that in the appropriate way, it will build up back pressure, and that's not a good thing. The data in this graph from a 100-hour cycle that we've done, and it'll become quite apparent why only a 100-hour test demonstrates this, is that when we get to 50 hours of operation in terms of back pressure build-up, it's the same at 100 hours. So it reaches stabilisation condition where the system is able to store and regenerate and run for an extended period of time. That back pressure increase is not significant. It's of the order of 4 kPa, and typically in a whole exhaust system there's about 30 kPa. So it's not a big increase, and it's detectable. So from a control system point of view, you're able to detect that change and know that you're toggling between clean and not clean. So stability is demonstrated. The other thing that we've demonstrated is if you do get the opportunity to run high load, for example, if you're climbing out of the drift, then you will burn off what has been stored and stabilised. So you will get back to baseline zero with a bit of hot temperature work. Now the cycle that we used here was the ACARP developed transient cycle, so that was looking at the real industry cycle, not some synthetic artificial cycle as the way the machine was operating. In terms of surface temperature, instead of having a proof of concept system, we've now encased this in an explosion-proof metal structure, and I'll show you a picture of that in a moment. The thermographic imagery shows that it's temperature compliant on the surface. We use water cooling at joints, because wherever you have a joint you will have metal to metal, and one side of that metal to metal joint needs to have some cooling in order to draw away the heat. But the insulation works quite effectively on all other surfaces, so any extended surface we're able to wrap it in a blanket and keep the heat in, which is good for the catalytic processes. There's a picture of the crew, both the orbital crew and the Centennial crew out at Newtown in New South Wales where we conducted our surface trial. There's the system again, and the CAD drawing there showing what's inside the instrumentation panel. So once you remove the cover, there's a bunch of instruments there that pay attention to what the DPF is doing and make sure it's all working appropriately. The core of that instrumentation system, or the onboard monitoring, is a little computer that basically monitors a number of functions. It monitors pre-diesel particulate filter conditions, temperature and pressure, and post-diesel particulate filter conditions, again, temperature and pressure. And these are the basics. They're the minimum things to determine the differential pressure across that device. Is it building up some back pressure? Has the gas going into it been of the right condition and temperature, and am I running in a condition that's going to be unfavourable? And the post-temperature there is to make sure that we're not having any thermal runaway or any adverse conditions where we're chewing up too much stored carbon and all of a sudden we're having hotter gas temperature than we expected. The real insight into what goes forward and what may be technology that gets adopted is real-time monitoring of NOx emissions and real-time monitoring of particulate emissions. So in various jurisdictions you have to monitor these on a monthly, weekly or 3-monthly basis, but if you can do it at source and know that there is or isn't a problem as you drive the machine, then you don't have to wait for an answer after it's been too late to do anything about it. To demonstrate where that technology is at, it is available on on-road applications. So you buy a truck now, it'll have a NOx sensor. Passenger cars have had NOx sensors for the last 10 years. Particulate sensors have been out for a couple of years in the on-road environment. There is no convergence in what that technology is. We have picked one particular technology, what we believe to be the simplest and the most robust. In terms of NOx measurements, driving around the Newtown mine, this swarm of bees essentially shows you different readings at different time, and you might say, well, I can't understand anything of that. There's a lot of information there. How do I know if it's meaningful or not meaningful? When you apply a filter for it, and the filter basically is to determine, okay, I've been at steady state for a few seconds, I can trust that number, I'm not jumping in between points, and then you map it across to the red points there, which is data from the dyno, you can see reasonably good correlation. So a bit of a filter algorithm on the real-time data can actually give you a great predictor of what your NOx tailpipe number is as the machine runs. If that number moves from baseline, you know you need to do something. The other sensor we had on site was the particulate monitoring system, and that's a resistive element type 1. So as it carbons up, its resistance drops because its conductivity improves. Fairly simple technology. It then regenerates itself, so it starts again clean without the conductivity and measures itself again. It's more a go, no-go gauge. It's telling you if the particulate filter has failed for any particular reason, rather than telling you if the number has moved by 5% or 6%. So it's really a scale of change rather than a resolution of change. If everything's compliant, essentially you're operating under the 1 milligram per cubic metre basis. If you see an excursion, for example, you may have had damage to the system, maybe it's cracked, maybe it's had thermal runaway and it's now porous, then you'll see a huge increase in particulates and the sensor's able to pick that. During the trial, there was no incident or excursions beyond the 1 milligram per cubic metre. So in summary, the project has been quite a successful demonstration of collaboration, collaborating with industry and collaborating with ACARP to bring good minds together into the one project to see, okay, this is new technology, can we apply it to a new playground? The first project demonstrated without a doubt that the proof of concept capability was there. The second project has presented some challenges in how do we industrialise that and how do we commercialise it, obviously ultimately to build it to a price that the industry can afford, and there's a good payback over the other solutions that are currently being implemented, with the potential for adopting further things such as runtime emission monitoring. One of the walkaways from this is the drive cycles that are used to characterise machines, and these apply not just to this particular project but to the development of any engine technology. That methodology of understand your machine, develop a solution for it, go and work with the sites to make sure that it proves itself out is a handy tool to remember. And I believe the collaboration has probably been the best experience for us. So I'd like to thank ACARP and the industry itself for sponsoring the ACARP program. I believe they're up for renewal for the next 5-year tenure, so I would encourage that. Thank you very much.
Okay, so thank you very much, Nick. We've probably got about 3 or 4 minutes for questions. I'll take any questions from the floor. It's beyond me, this diesel particulate filter stuff, so it's not getting them from me. Where's the fitters in the room, everybody?
Morning, Nick. Tom, I'm the GM at Grasstree. Just a question about the serviceability. So you mentioned that you wrap this thing in a thermal blanket to keep the temperatures higher and whatnot. So what does that mean when you take it back to the workshop? Do you have to have a longer period of cool down before fitters can get back in there to change out, or is there going to be time imposts on that side of it?
Yeah, look, it's a good question, and certainly the insulation does keep the inners warm. It could take you 3 or 4 hours for this thing to cool down. The intent is it's tamper-proof and not designed to be regularly surfaced, and that's part of the industrialisation project. Is we're aiming for a Code D change-out, so aiming for 2,000 hour service life as opposed to once every 8 hours or once a week or once a month. That is a nice milestone to set. The core technology that's inside our diesel particulate filter on road achieves about a 4,000 hour life, or 400,000 kilometre. The mining environment's a little bit tougher, the temperature conditions are a little bit tougher, vibration and other things have to be considered. Fuel and oil selection are key requirements, so it's beneficial to use low sulphur fuels. So Aramanga UMF is probably not a good choice, and low ash oils are good as well. So if all goes well, it's usually the oil that hurts you. Even a low ash oil will limit the time that you have to change it, because a low ash oil is a metal oxide and you can't actually burn that off, you have to blow that out. So that's the main service increment that comes out. We'll be happy with 1,000 hours, 2,000 hours is a nice target, and that's what we're aiming for.
Thanks.
Morning, Nick. My name's Nick Scully. I'm with the DRNMA. Mm-hmm. You mentioned a little about commercialisation, and it was a bit more work to be done there. What encouragement is needed to get the commercialisation kick along?
Yeah, a good question. Having worked in technology for 20 odd years, that is the hardest step sometimes. You've got to have a brave first mover, and some of these companies that are working with the project, Centennial and South 32 for example, are keen to have their OEMs adopt that technology. One of the OEMs has been part of this journey already, so PPK Group, who make the coal tram, predominantly sold in New South Wales from what I understand, have been a sponsor in kind in terms of engine technology. So they've been part of the journey and perhaps have an understanding of that's the next step that they need to take as well as a solution provider both to their industry and also as competitive technology to others. Sandvik, and they're the custodians, I guess, from the old Ironco machines. They are joining the program for this final stage of 26070 as we look to demonstrate that what we've developed thus far does apply to them as well. That commercialisation step, from my experience, comes from having the OEMs on board. Orbital as a company is able to make the diesel particulate filter, but we're not necessarily able to tell people you must fit it. And that comes voluntarily from OEMs and miners saying, yeah, I think this is the technology, I think it's disruptive enough, and I think it is at the right price that the payback's there to do so.
Thank you, Nick.
Okay, Nick, thank you very much. Put your hands together for Nick. Thank you once more. 1 minute for the next session.